let's continue our math adventure. We are learning number theory, which is giving us the tools to work with fractions in a much more efficient way. So today we're going to work with something called greatest common factor. And the only reason why we use greatest common factor, it's to reduce fractions. So if we take a look at this fraction and we have 32/48, well, in order to find the greatest common factor, what I need to do is go back to the factors of 32 and the factors of 48. So I know that when I multiply 1 times 32, it equals 32, or 2 times 16 is equal to 32, or 4 times 8 equals 32. For 48, I have 1 times 48, 2 times 24, 3 times 16, 4 times 12, or 6 times 8. But I want to find the common factors. So when I go and look at the common factors, well, we know all numbers are going to have 1 in common. But these two sets of numbers also have 2 in common, they have 4 in common, 8 in common, and they have 16 in common. Therefore, the greatest common factor is the biggest number. And sometimes we'll say that as GCF is equal to 16. So we'll break that down. Now, what does that mean for us? It means if I want to reduce the fraction 32/48 in one step, all I need to do is divide by the largest common factor those two numbers have. So if I take 32/48 and I divide the numerator by 16 and I divide the denominator by 16. 32 divided by 16 is 2. 48 divided by 16 is 3. Therefore, this is the lowest term or equivalent fraction of 32/48. Now, if I had divided by any of the other common factors, I would have reduced it and I would have gotten an equivalent fraction, but I would have had to reduce it a second time. So if I took 32/48 and I divided it by 2, 32 divided by 2 is 16, 48 divided by 2 is 24. Yes, it's an equivalent fraction, it's just not in lowest terms. So we're going to add on to that because in pre-algebra we know that we have variables. So let's change our fraction here and let's add some variables in there. Let's say we have x to the 4th power, y to the 3rd power, z squared. And let's add x squared, y squared, z. Well, this seems overwhelming to look at, but really it's all of the same concepts that we've been learning. However, the factor rainbow starts to break down because it's less efficient to work with the variables. So we're going to go back to our prime factorization trees. And we know that we can take any number and we can break it down into its prime factors. So if I take 32, I'm going to look at these factors and I'm going to think, what do I want to start with? Well, I know 2 times 16 equals 32, and I know that 2 is prime. And if I have 16, I know that's 4 times 4. Neither one of those are prime, so I'm going to break that down to 2 times 2 and 2 times 2. So the prime factorization of 32 is going to be 2 times 2 times 2 times 2 times 2. Now when I'm reducing my fractions, I never want to use exponents. So no exponents ever when we're doing this. You're going to want to write out your whole prime factorization. Now I'm going to do the same thing for 48. So I can choose any two factors. Let's do 2 times 24. 2 is prime. 24, let's do 2 times 12. 2 is prime. Let's do 2 times 6. 2 is prime. Let's bring 6 down to 2 times 3, and both of those are prime. So the prime factorization of 48 would be 2 times 2 times 2 times 2, but then it has this 3. And so I'm going to pull the 3 out here because what I want to do is I want to take and pull down all the bases that are the same. So I see that both 48 and 32 have a set of 2's in common. So I'm going to bring down one set of 2's. And they have a second set of 2's in common, and I'm going to bring that set of 2's down. And they have a third set of 2's in common, and I'm going to bring that set down. And they have a fourth set of 2's in common, and I'm going to bring that 2 down. But notice this 2 has nothing in common, and this 3 has nothing in common, so I'm going to leave those alone. And if I go back and I multiply those back together again, it should give me my GCF. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So the prime factor trees are a second way that we can find GCF, and we don't have to rely on the factor rainbows. Where it helps us with the variables is because I can also now add in my variables, and just like before, I don't want to use exponents. So I'm going to add in 4x's, 3y's, and 2z's. And I'm going to add in 2x's, 2y's, and 1z. And just like on our numbers, we're going to pull down what they have in common. So I can see that they have a set of x's in common, and I can see a second x in common. I can see a set of y's in common, another set of y's in common, and a set of z's in common. So that means that the GCF is actually 16 x squared y squared z. And if I took this fraction here and I actually divided it by 16 x squared y squared z on the top, and I divided it by 16 x squared y squared z on the bottom, it would reduce that fraction in a single step. That is the whole reason why we're doing greatest common factor. Now, are you up for the challenge? Let's see if you can try this.